So it's now 1:45, so I'll start the next session and introduce Chris, who needs no introduction. He's a man who has fingers in many space pies. So I'll let you go, Chris.
Very good. Thank you very much, Jim. So, yes, nice to see everyone again, and welcome to the 100th edition of the Chris Bridges Show. I'm here today to talk to you about really some of the developments that are kind of outside perhaps what you've seen the talks on about previously. In the last few years, we've been talking about ESEO, how our students have been involved in that particular ESA program. But actually, I run a research group, and I have a whole swathe of undergraduate, postgraduates, and staff that are working on all sorts of different things. And I kind of wanted to touch on really some of the things that have been really good developments that's come out here that I think this community will find particularly useful. I wanted to start with really to sort of give you an intro, just one particular topic that I'm going to start on. So it's going to be about showing off hardware and showing off the sort of things that we have at Surrey and the things that my students are able to do. But really, we want to start with one of Alex's work. So he's one of our students who's been working on GNU radio stuff. So those GNU radios in the room, Bart, Ian. Okay, perfect. Okay, Mike, excellent. So this is some new blocks that hopefully will open source as well, about using GNU Radio as a full-blown simulator and actually having all the extra features that you needed in it. Dionysius, he was working on our REST onboard computer, in fact building a version that actually works. A team has been helping us develop and then debug all of the different things that we need to do on this particular mission. It's quite a complicated mission. And he's been able to debug some stuff. And Jorn finally is then helping what we're doing then on the imagery and the imagery processing. We'll talk about some of the ground station additions that we've had, the REST mission itself, and perhaps some of the things that maybe G0MRF David and I are looking to coerce ourselves into doing at some point in the future. Shockingly, there's this buzz around a satellite called QO100. You may have heard of it. Okay. A few mentions yesterday. One of the things that we were looking to do is when we were building our own ground stations, and certainly when we are looking at undergraduate students, and then those undergraduate students stepping up and going into their master's program, is the element of science that goes into them. The way that I tend to see my MSc students, certainly as they're going on, or their MN students, is that they need to be thinking about how they're becoming future scientists. A proper prediction. Theory that's underpinning then that prediction. Having a methodology that then they can go and test things with, create an experiment, that then they can then properly analyse and be critical, whether it's qualitatively or quantitatively. It's very different to a typical sort of undergraduate project, which is really just looking at being a good engineer, doing some really good engineering, managing your own time. The MSc is that sort of small stepping stone to consider whether or not research is something for you, whether or not being a lot more critical and being a much more thought of designer is the sort of thing that you wanted to go through. And so that's often very, very challenging when we build our spacecraft and our space missions, because where does that element of science really come into it? And the one thing that I set for Alex was really about going, well, we have these things, the Yanking sort of very famous link budget Excel sheet. For those of you that don't know it, please look it up. It is best part of 30 pages of Excel sheets where you have to then collate and put all your numbers in that can then tell you whether or not your system links essentially work or don't work. Okay, a lot of these things are based on principles, assumptions, and other such things. And in particular, things like your free space path loss, cable connector losses, all of these sort of things, antenna polarization, blah blah blah. All of that stuff kind of gets added in, but there are some still things that we could perhaps do better and to feed in through a lot more of these equations. Whether or not we're looking at the amplifiers, the losses, rain attenuation, what happens with the sun, actually what happens with scintillation. There are a lot of other models, especially when we start moving up in the bands. This Excel sheet maybe doesn't do everything we need it to do. And when it comes down to it, we can implement them actually in a whole different number of ways. We actually went through, and Alex went through, and actually found out all the equations that we could find in his thesis relating to linearity of amplifiers. or related to whether or not how you're looking at system noises and how these gains then fit and attach to each other. How then impedances are worked out, and how you can then work that out when they are then collectively put through together as a chain. And some of these things we can actually write analytically, which is great, or semi-analytically, through classic equations. And some of them we're going to have to look at really through tables, and coming up with our own either analytic equations to then linearize them, or just flat out having tables in them. And so what the challenge was really is then, can we use other tools to do this, or do we add them to an Excel sheet? And the decision was made really for Alex, is that he wanted to know more about GNU Radio, and I was like, sucker. Okay. And so what we ended up then doing is we sort of wrote many, many blocks and coming up with new blocks just to really build GNU Radio as an actual simulator. It's actually what it was made for to begin with. So building mobile communication simulations and to be able to see, does this work, but in a much more dynamic environment. So if your noise floor changes, if you want to test things sweeping in and out of your signal, you're not doing that on an Excel sheet. Okay? You can do these things in GNU Radio. And so we came up with a whole new series of blocks with the transmitter adding in resistance reactance, the actual noise temperatures of each of these systems. Because as soon as you start adding these things in and your noise keeps going up along this chain, this really starts to be a problem, especially when you're starting to build then precision instruments. Whether it's a precision RF instrument, whether it's optical, whether it's audio, how the noise then propagates through all of these systems really does affect your bottom line. For the coax cables, we've got those. Those are kind of in the equations already, but adding in things like your system temperatures as well as sample rates, just to understand limitations of what you can push down different mediums. Again, not all fully captured. Same thing for the amplifiers, transmitters, same thing for the receive chain as well. There are models available for the channel. There's like GR Leo is one. There's a few other models so you can actually do your own channel estimation. So once you've kind of built up a transmitter, cables, amplifiers, cables, transmitter, antenna, these sort of things, you can then add that to then a channel model. But interestingly, then you still get your noise temperatures involved. You can then decide really what you're doing and where you're going. In this case, we're interested in QO100, so a fixed position now. So we wasn't integrating any orbit dynamics, but actually that's quite trivial now. Really what we wanted to focus on is actually could we match a simulation in GNU Radio, which number one, vaguely matches what we see on the Excel sheet, which actually works out roughly the same in reality. And again, doing that all in a scientific method as we would expect a master's student to be able to do. So you can see there all of these extra features that have been added in, understanding whether or not things are linear, what the system noises are of each of these parts. The only block that we're reusing is actually this log power plot that is already one of GNU Radio's kind of features, but the rest of them, actually Alex then went and built all these blocks himself. And so what would such a system look like when it's put together? Well, I mean, for those of you that are unfamiliar with the sort of flows of what these blocks look like, you're going to have a transmitter which will have some signal source, which may have something complex as a source. You might end up wanting to use Danny Estefis's GR satellites as a front end. You know, there's lots of different things you can play with here as soon as you start getting the blocks in. For us, we're interested in perhaps, the classic, BPSK 2,500 bits beacon, because it's something that we can go and measure. It's there, it's a constant, it's used as a reference on QO100, and it's then a good reference and a good baseline for what we can use to test this simulation. But we can then push things through each of these different models, through a channel, back through a receiver, to then understand what we get out, and have then a comparator part as well. So you've got your green transmit, your blue then models as it goes through, and your red coming in. And you can add things like bias T block, physical representations actually of your system. And then the purple block there is the things that we're measuring. So, what do we find? Well, we find really that from our reference signal, you can get pretty good analysis, but it depends on a couple of things in the way that you measure it. So with all of these sort of signals that you're coming in, you end up having a problem, or not a problem, a correlation with the way in which you're sampling and the way in which you're filtering your final signal. And really what I wanted to focus on your attention really is that we know what the BPSK signal should look like. We know then theoretically what the link should physically exist at. These things known pick your book, okay, for communication theory. But depending on really how you're measuring it and what power you're physically measuring across what bandwidth, which is directly related to your sample rate, you get kind of different results. And so if you are actually using an alpha of 0.6, where this is something that is actually quite wide, this is essentially quite a harsh roll-off if you think about it as in a sort of filter point of view, then actually you end up having quite a lot of noise in. And does it actually fit the theory? Yeah, broadly, if you were to take the sort of mean averages and things. And of course, if you then over-constrain it and over-filter it, it just takes longer to go up. So you can kind of see this as almost an integration time type of problem. Okay? You need a certain number of samples to be able to effectively make your calculation within a certain level of statistical confidence. The question is do you want loads of samples quicker, or do you want to do it steadier and get to that point sort of slower? Okay. By the by, these mean the same thing. But you can look at this in a couple of different ways and do the statistical analysis. We know what the theory should be. We can see the peaks. Even if you were to do it quick and dirty, we can see that. But there's all this energy here that is really where things like your additive white Gaussian noise, your system noise of your system, is going to start to play. And shockingly, as soon as this alpha levels or your integration time steps are increased to a point where then you're filtering, you can start to see then where things start to collect when you have much more harsher sort of environments. So what does this do when it comes to then actual accuracy? Well, if we have certain levels of alpha, we can get, 0.6 alpha is just a massive filter. You're taking in essentially too much. But for 0.1s and anything less than that, we're sort of fractions of a dB close to the original signal that we want for theory. Okay, good first steps. Good first steps that he can go to. He's done a small experiment. He's actually gone through, made predictions. He can relate it back to the theory. Okay, what we've done here is essentially skipped, 90% of the equations. Okay. What's the next thing to do? Well, the next thing that he needs to do is then start adding much more physical parameters. Let's start adding in all the QO100 stuff. So bringing in stuff straight from the specs, straight from references, so that we can then go and add all of the right things that we see. Okay. And when we actually go ahead and do that, we can then do our own simulation. And we can do the same sort of plots as well, when you can look at, for instance, just a dead carrier. And we were off by 0.6 of a dB. But as soon as you then go, well, hold on a second, we should take perhaps the 3 dB down from this. Really, if you're doing most DSP, just to actually capture really where the peak of the signal is, it's almost bang on. I think 0.0014 okay, of a dB. Not bad. Okay, not bad. So we ended up then going that and doing that a bit further to then start to then go, okay, let's push more signals into this. Because now that you've kind of got a simulator and a channel, which should work, which we've known to prove in actually a couple of ways now, what can we physically do? And so he built an interface for that. This is just a SailSat2 interface, where you can set your uplink gateway, your satellite, your downlink, and add in things like your azimuth, your ranging, your polarization corrections, to then calculate these things theoretically as per your system. So the things that, for instance, he hasn't modelled in here are things like if you've got circulators, if you've got more than one antenna plugged to the same things, splitters. Okay, theoretically, some of these things, we assume, minus 3 dB. Okay, well, that's based on a system noise. There's an actual linear relationship to that, and you can physically go and measure it. And of course, you can go and do these things, and of course, these sorts of tools can then be used to then monitor how your own ground station is performing. You should know what it physically is doing, and if it starts to deviate, well then which part of it has gone wrong. So we've got all these different options here. So what's the next thing we need to do after this in the scientific process? Well, we've got to do it. So I was helped by David Bowman, who's probably still in the room somewhere, sitting there, wherever he is. Who essentially we were working together in the space station doorway, and we knocked up this bias T, and he goes, yeah, no, this should all work. You've got the, you've got the LNA, you've got the dish, 60 centimeters, and I'm going, this is not going to work. And he went, oh, you'll figure it out. Helped us sort of do a bit of the bias T bits, and had to get on the road because M25. Am I right? And by the evening, we're picking up narrowband signals through my office window, through trees, and I'm like, this is bonkers, okay? Utter bonkers. Because most of my work has always been in LEO, and I had to just make several phone calls to tell people how bonkers this is, that this stuff is actually working through my office window. The next step, of course, is my student needs to go and do it. And exactly as Akeem said sort of yesterday, 12 euros LNA, sub 20 euros for the actual dish. He's like this, yeah, no, I'm doing it. And he did. Within a week, he sent me this kind of photo where he's sort of like going, yeah, and he's sort of taking his own readings. Okay. And of course, there's the step on from that, which is then going, okay, let's build your own patch. Let's put it all together. All again in sort of the 1 year sort of master's sort of thesis, and he can then start to get things going through. What's really good is we can then go, and when we actually measure things, we know what a simulated beacon needs to look like, 11.6 dBs, versus the Excel sheet, which actually says 16 dBs. It's quite a bit of a difference already. And then what we actually got, which is 13. And so there is still some error involved in that, either in the measurement, either in our alpha or H values, the equations or the tables. There's more to do here, but for an MSc student that can go from actual equations to then putting them into a system that then they can go and try things out and compare it with then real measurements, okay, is just a wonderful thing to do. And I think QO100 is just one of many platforms that they can do it on, and it makes his life easier, because who wants to rotate a dish in Leo, he says. So, okay, so the next thing on from that, and that's Alex's MSc. He's gone back home now. The next thing, of course, is to then start adding it to perhaps some of my more bigger equipment. So we have a 3-meter dish down at Surrey. This is Richard Duke. This was my old MSc student, who's now one of the ground station managers at Surrey. And this is us sort of putting it on together with one of our other feeds that we have on the dish. This is M0GSM. And we essentially were going, okay, 3-meter dish time now. Let's see what we can kind of do here. And we could get the feed fully coming in to our ground station. Essentially, it's on our 5G building, which is, I'm going to say 100, 200 meters away from us. So we actually have it coming down to a USRP. It comes then back over IP, over UDP, and we stream the actual stuff back into our ground station. And Richard has spent a long time, essentially, for a lot of our CubeSat missions that we've done in the last 7-8 years, to then build up these sorts of tools, and in particular, all of our ground station ones. And so we use a mix of back-end Python, and then it's PHP, and then it's all HTML5, really, that then builds it up. He's very much wants to use modern technologies inside the ground station. And of course, it's really great that we've got, again, utilities like the WebSTR that Goon Hilly provides and AMSAT-UK provides, because then we can then just double match and what we see on these things. Things we haven't done yet. We haven't played around with polarization. We haven't played around with things, but when you've got a 3-meter dish, kind of doesn't matter. Okay. I am bragging. But we can go ahead and do this. People I'm not going to tell you about. This is Richard again, very happy. First time he'd got a geo signal coming down into the Space Centre. Also me very happy, because it took ages, health and safety. Zach as well is doing experiments on FEC encoding for his PhD. And so we've been doing some weird and wonderful things about ranging, around combining of different codes and weird mathematical identities to do just weirdness. Okay, I'm waiting for this stuff to be published with Zach, so that's one for another day, I'm afraid. You got away with that one because there's a lot of equations. But where does this all go, and what utility do we need it for? I will have last spoken to you about the REST mission, I think in 2005. And in 2005, I would have been telling you about a mission that we have with Caltech in the USA, IIST in India, and NASA JPL to then build up essentially a configurable satellite. And really what we were doing on this system was having a satellite that goes up and essentially in 3 pieces. And these 3 pieces are one core piece, which is roughly a 12U, and then we've got 2 3Us on the side, and those 3Us can actually dock and undock and move around. And so we've got lots of different floating platforms and been developing algorithms to then go ahead and build this rendezvous and docking mission. The actual pieces that Caltech provides are these mirror boxes, and these are deformable mirrors controlled with very fancy piezoelectrics that I know nothing about. We're essentially providing at Surrey a lot of the platform stuff and the pieces that does the docking and undocking. But different optical configurations for the telescope gives them very different results. And of course, at the same time, we then get to test docking, undocking, relative motion, rendezvous, close proximity operations, pick a whole swathe of thing, okay, that needs to happen in that arena. So we're testing a lot of these boundaries. In 2015, that's only 10 years out, I showed you the sort of version 1 of really what our onboard computer was going to look like for this. And this was built by a student called Oliver. And Oliver essentially we designed a dual redundant Raspberry Pi compute system. And these Raspberry Pis could then operate then either as hot redundancy, where they're both on and they're both actively doing the same thing, so that if one goes wrong, you can switch, or you can operate them in cold. It gives you a lot of options on that. What we did with this first development is really just the initial computings. There are things that are missing on this. Good example is the holes for the thing, you can see here. This is an undergraduate student project, might I add. So he did this in pretty much 6 months, as well as doing all these other modules. Really great achievement. And really what essentially the next student then had to do, Dionysius, he essentially then had to rebuild some of this and add in all the pieces that we'd forgotten. So things like the holes, okay? You'll notice here is one of the big things. We had an alignment as well in the SODIMM, so we could fix sort of minor revisions of these sort of things. Now, for those of you with the keener of eye, okay, you will notice then that we've perhaps got a big chip here, lots of circuitry, switch, these are what these are, and then there's a weird looking bit here, which is essentially an RF system. Okay, so we actually have an intersatellite link that sits here. This is an RF part. This sits on a completely different set, and that will be then an SMA connector or SMB connector on that. The actual finished board, again, he did undergraduate project, folks. Looks like this, where he's actually been able to fit it all in, and you can see the back side of this. And a lot of this monitoring circuitry that we have on here is essentially an FPGA or CPLD, some programmable logic here, which essentially acts as a router. So actually what happens is we get I2C coming in, we actually have it coming in from the platform, but also the Raspberry Pis are masters as well, because they actually control some of the payloads as well to actually do the rendezvous and docking maneuvers. And that then controls with switches to the RF systems, because we have 3 sets of these computers on each of the different satellites. So these are acting as not only our inter-satellite link, but really as payload managers. And we call this essentially the payload interface computer. When the satellite is kind of as one, you can just use one of them, but as soon as we start docking and undocking, you need to activate at least 2 of these, so they can do relative motion, they can do ranging, they can do all sorts of small pieces in and out of the satellite. So we're actually looking at some good hardware here. Big steps for these sort of things that I wanted to sort of highlight. This was a good day. Okay, there have been bad days. We'll concentrate on the good days that I wanted to highlight in this picture. One, it says program success, green lights through the JTAG, really low power. Let's have a zoom in. What we'll actually have there is on 3v3, we're drawing 95 milliamps, and on 5 volt, we're drawing 7 milliamps. Okay, so the CPLD and the FPGA design that we'd had to be just ultra low power, just do I2C routing, switch things as and when we need to switch things, that all worked. Okay, and it was as low power as we expected it to be, because as soon as we start then doing rendezvous and docking maneuvers, shockingly, that's quite power intensive. Okay. Program success, green lights, great. Things get hot though. Okay, so there is one issue that we need to resolve where we're hitting 50 degrees C in air. Okay, when these things are running, so we are running these things quite warm, and so what we need to do is actually we'll put a copper strap heatsink, like we've had to do on a lot of our other missions for hot devices. But again, things that you can kind of go through and do. So Dionysius then left me to then go and do finance stuff. Because money, right? And her team essentially was stepping in. And her team was in my VHDL class. This is her team here. I've tried to show pictures of them where I've got them, because really they're the stars. They did a lot of this work. And her team essentially was figuring out how I2C was working, really from a 101 point of view. Okay, so for those of you that are either on the stream or in the room, but know, love, hate, pick your relationship with that particular data bus, will have seen many of these diagrams before. As I said, our CPLD has multi-master I2C. We have a payload I2C bus. We have our own platform I2C bus. And we use these things to route information very quickly between a lot of the modules. And we use it as well to switch between things and to know how to control very small parts of that design. So with our I2C FPGA, doesn't just act as a router, it also is a switcher. It monitors heartbeats. It monitors the power levels. So a lot of the back switching that you saw on that complex PCB earlier actually has a lot of power monitoring circuitry itself to then know if something has happened. And initially, really, we were just trying to figure out what was happening with the I2C bus, checking the VHDL firmware. That was getting pretty tight, and we were wondering whether or not there was a timing constraint that was missing, whether or not the operating system or the config had changed. As we remember, this is 2015, it's 2019. OS has changed. The Raspberry Pi versions have changed. Whether or not there was something to do with that, or whether or not there was just a part that was wrong or a part that was broken. So, by show of hands, who reckons it was the VHDL? 1. Who reckons it was the OS or the software config? Okay, maybe about a dozen. Who reckons it was the parts? About the same sort of number. Bottom line, yeah, it was the parts. It was a 2.2 ohm resistor that should have been a 2K2 ohm resistor. Okay, there were 5 of them that then just ruined everything. Okay. Soon, yeah, finding it, awful. Okay, going and measuring loads and everything. We didn't really see it on a lot of the power circuitry because there wasn't much of the drop on it. But for the bus itself, yeah, big headache. And so we were testing that new board together with other Raspberry Pi boards, together with even just basic Arduino type stuff, just to go, all this multi-master stuff should just work through this router. Okay, and eventually we got it all working, lovely timing diagrams, hideously low powers. Okay, wicked. So that's kind of where we've got to on our computer. We do need to spin the next version, because as I said, we've got to put these heat straps on, and we're actually taking off one part as well, because the payload provider has de-scoped something. So I can take parts off, which is great. So we'll do none. I've got to build 6 of them by March. Okay, so this time next year, maybe I'll have one. I'll bring one here if I've got one spare, because I've got to send them to the US and to India. The main system that we're working with this particular computer is actually a LiDAR that has an optical sensor as well as a laser as well on it. This is before we cut off all the audio stuff. You can see behind in the background some of the unit blocks that we're building up for R3U. But this particular LiDAR as well allows us to do 2 different things. Because it is a laser that is doing reflections and getting a backscatter to generate a point cloud back on an optical sensor, well, actually, if you know what the software's doing, you can just use that optical sensor as just an optical sensor. And so what you can do is then interleave them. Because as relative pose and motion changes, this becomes a problem. And I'll kind of get onto that in a second. Yawn came onto the project to help us then develop that, in particular, understanding how the modes would work between both optical and depth type point cloud sensing. For the laser system itself, the peak rate that we were having things come in, especially when it was very close to us, was about 60 frames per second. And at longer ranges, it would drop down to about 30. But he essentially was able to change part of the software by moving from a conversion of one particular color format to another type of color format, which didn't really cost us anything. And they got a 4 times improvement. So we were able to do range and pose estimation at around 12 frames per second. Okay, not bad, because there's actually quite a lot of processing going on there. When it came to the optical ones, well, for low resolutions, it's a sort of 480 sort of things. That was at 30 frames per second, and at high res, when these things are much bigger sort of frames, it's 5.2 frames per second. Much slower. And we were drawing peak memory of about 12 meg, less than a meg of rough stack. We did real profiling on this just to understand how it would work, and how it would work, importantly, when we interleave it with then control signals. So yawn, after we'd kind of done that, we then needed to go, well, what is it? What's the environment it's going into? And I wanted to show you this video here from the Swedish Space Corps, not to be confused with Surrey Space Centre, and DLR, and this mission is called Prisma. And Prisma is a mission that had 2 satellites, one called Tango, the other one called Mango, and they were essentially doing relative maneuvers around each other. They were doing this particular mission with, you can see how many frames per second this is. This is barely kind of 2 frames per second sort of information. But these sort of ones, there's some really good ones online, especially of ones where you've got one lighting condition on one side. As soon as you go in front of the Earth, it's completely different. You change the other one, the shadow is not where you thought it was. If the satellite and the sun are both on the same thing, they're both shining, they both look white. And so then the target is lost. And so optical doesn't just work on its own, LiDAR won't just work on its own, and you kind of need to use a subset of both. How big is this satellite? How deep is it? Can anyone see? You can't. Okay. Unless you already know about it, this exactly is the sort of problem. There's about 3 or 4 videos that demonstrate this really well on YouTube. Check them out, because it's just stonkingly hideous. Okay. I'm actually going to be using, in the future, neural networks to kind of train this to then understand when the environment changes. But the lighting condition, what reflections are coming off where, well, it's still an open problem for us. So what do we need to do? Well, we need to start to build our own, and for Yawn again to test some of these theories to find out how it would work in reality. So we used MDF and Home Depot type of things, and bought some solar cells, some really cheap ones for, I don't know, $3 or something, to then actually just build some models to start to get some characterization of really what this would look like in the flow. In particular, we want to know what it looks like when we're swamped, when we've got diffuse lighting, when things are occulting, all of these different systems, because those are the things that we're going to see. So we actually used the Centre for Vision and Speech and Signal Processing, which is another lab that we have in the University of Surrey, and they've got this big sort of audio room and camera room where they can do lots of very fancy things that they do with the BBC and I don't know, Pixar and stuff like that. They work with those sort of guys. But I was like, can I use your lab please just to take a picture of this shiny metal box, and I need some lights just to shine at it. And they're like, yeah, fine, is there anything else? And I'm like, no, go away. And so we ended up having setups that looked kind of like this, where we had a trolley on one thing. Little do you know that right under here, there's Yawn is kind of laying down, slowly turning it around, okay? But we wanted to have sort of a very pitch black sort of environment. But you can kind of get an idea of the sort of imagery that we would kind of begin to start to take to, again, see what these things would look like. You can just about see it here because there's so much diffuse light coming actually off the back of the environment. If that went on for much further, you wouldn't be able to see the back of this at all. Which, again, is the sort of thing to try and emulate and simulate. And to actually build up data sets ourselves to go and then test algorithms with ourselves. 9 times out of 10, if you're building neural networks or any machine learning things, data sets are key. So for the vision system itself, what did we find? Well, we found lots of specular reflections, lots of resonances, and as soon as you start to do edge detection on a lot of these things, it can fall over pretty quickly. Okay, but for the depth system, that wasn't so bad. Okay, when you look at it in optical, it doesn't look really good. But what's wonderful here, okay, I'll put some emojis on it because this will be important later, is that for the depth flow, we go through a binary mask, we dilate it, erode it, do some corner and edge detection in some fairly classic ways. There's a particular way that we're using in this one to get our range and pose. And of course, what we can do is we can take lots of samples, we know what our truth is, because we had a separate camera system that was working, understanding our truth, to know what then the differences would be for different angles, different ranges, and working out the error. Bottom line, depth camera, amazing, okay, except when it's getting directly pointed at by something that might look like a sun or another star. But more often than that, yeah, heart faces, sweet. When it came to the optical side and just using the optical cameras itself, this is kind of very common, where you can get sort of a mask, we can dilate and erode an image to then understand where our corners and our features are, but then when it came to precision under kind of all circumstances, not so good. Okay. Horror face. Okay. With our optical flow, we're generating masks, we're grayscaling things, we're working out connected features, we know what the object is and know what it needs to look like, before we then run that through then edge detection to get our range and pose. But you can see we actually had quite disparate results in a lot of places. Similar places again for certain types of reflections off of corners, but much bigger room for error. So optical flow, thrown out. Okay, don't need it, it's really bad. And in fact, it probably, if you was added into your control loops, may end up having liability. It might be information that you still want to use, but let's just see what other sensors and things we can use. We're actually going to add LEDs. We found that the following on project done by Professor Underwood, when you use LEDs, we can then put an infrared filter on it. We can then just run those things together with the LiDAR. And then you get then a really fine and precise things when you bring those two together. So we've now got a Raspberry Pi computer that's then sitting with then a unique camera system. The next thing is then to go, okay, let's kind of build one. And so some of you might have seen online that, sorry, we've been building and working with Raspberry Pis on another one of our missions. This is actually one that was done with SSTL and done with Chiara, who was one of our Surrey engineers, Sam, who was one of our ex-MSc students, and Alex Erlank, who was one of my PhD students, who then went on to then build these things. Pi Zero, some IMU stuff. We actually have the Raspberry Pi camera underneath. And what sort of images do you think you get from Leo? Well, you get something that looks like that. With this is 195 degree field of view. Okay, and we kick ourselves because there's a cable here. But this is the sort of thing that you can get of the Mediterranean. And so we want to use this and get, it's actually a much bigger picture, but the sort of outside edges we've cropped off because it's nothing, it's just space. But you kind of, with a 195 degree, we can point down and look at the Earth. And what we're trying to do is trying to get some internal resource to maybe look at the poles, maybe just to do it more, characterize it a lot more, because this works and it works fine. What does it look like in a video, I hear you all asking? This here is the UK. If we were a day earlier, it was absolutely, on that Friday, it was absolutely stonking. But we can get then really, really good. Is that playing? Oh, okay. I think it was just stalling. Let's just do that again. There you go. Buffering. But that's the sort of thing that you can get from a Pi Zero, and a regular Pi camera, with good engineering and good interfacing and good software. Okay. And SSTL have flown that as a payload just to demonstrate the sort of thing that you can do with commercial technologies. The usual thing that we like doing. And please don't go talk to them if you're interested about this as well. There are things that probably I'm not allowed to do or say around the testing and the things that we've done about Raspberry Pis, because I've had them in radiation and I've had other things. But some of that will be commercially sensitive. But I leave that question open. Get in touch with me and we can maybe work something out. Yep, 5 minutes, which is just good. And so that's really what I wanted to sort of show you, is sort of what's been happening alongside all the other things that I've been doing. And one of the things we want to do for this year is kind of push the barriers a bit more with a lot more of the equipment that we've got here. We've recently done missions with Raspberry Pis. We've recently got QO100. And we've recently got new FunCube hardware and software as part of the ASAO team as well. And so really what I wanted to figure out and work is could we build a payload that would be L-band up, X-band down in LEO, and use that as a ranging transponder. Okay. Again, these are sort of targets that I want to use for perhaps a future mission or a future payload, something that's going on to something else, that will then be used to educate my undergrads, my MSCs. They need a bit of bite, okay, behind what they're doing. Okay, I don't want to be another beep sat. I don't need to do some of these things again. It's good engineering processes, but we can do better. For the hardware itself, usual things. Smaller, faster, stronger, lighter, all the Superman stuff. Yeah. For the software itself, actually moving perhaps some of the things that we would usually do in a hardware device or some sort of other transistor configuration to do maybe software demodulation on chip, whether or not we can move to the digital, begin it to really start to look more like an actual SDR. The ASAO one does really all of our real SDR functions at baseband, and there's still not a lot of room really for change. It has fixed frequencies. There's only certain things we can do with it. Can we patch things? Can we patch our threads as we do things in runtime? I've done that before. It is as hairy as it sounds. I've patched a comms uplink over a comms uplink, and I don't really want to ever do that again in the way that I did that before. So what is the way in which we can do that? Again, capabilities that we will need to have in our AMSAT community, and techniques to use, or at least processes to follow, so that you can go ahead and do then bigger, better things, especially if something goes wrong. Can we then add things for flexible payloads and interfaces in the software? For the student size, is to really look at, again, using GNU Radio, GR satellites, pick your Python libs to then sort of go, okay, let's build something that can then work with this system, that works with it with a certain level of reliability. I'm talking about multivariate Monte Carlo analysis. I want to know statistically how something is or is not going to work with a certain setup. We've just given you and shown you a whole series of tools that we might have actually been using. We need to start using those in some real angry processes. With the downlink itself, you might know this call sign. Okay. Whether or not David and David can actually help us to come up with really what that preferred part is to work with a student, to then use our test facilities, our anechoic chambers, our thermal chambers, just to know what things will and will not work. And can we build a new patch that is L and X band? And we're actually then employing some expertise from another amateur that we have at the university that works in our 5G centre. He's our antennas expert that works on there, works on phased arrays. And I'm like, Tim, this is your bag, okay? Please help me do this, because I will have my work cut out for the top bits. And lastly, can we do something with maybe that follows on from Dr. Willis's good work in that sort of patch antenna? Instead of having S and X, can we do something with L and X in a similar way? Note, for those that are perhaps either on a stream or thinking about it, these are predominantly EEE computing kind of backgrounds. Okay? Except for the sort of antenna part, which you might be able to do mechanically and do things with in CST, which is a much more of an aerospace type of thing. I'm still predominantly looking around that, and we're going into sort of week 1, week 2 of my classes, and I see and meet aerospace students, they're kind of like, oh, damn, you know, maybe I've got this a little wrong. And the term aerospace, I think, still captures everyone still just because it has the word space in the title. Little do they know, not the skills we need, okay? It's not the skills that we necessarily need as much in industry as well. And with that, that's the future. This is just a toy that I'm playing with at the moment. Just for comparison, you all know the sort of SDRs. This goes out onto our roof, onto one of our antennas. This is essentially a Raspberry Pi that's running SatNogs. This, however, is an FPGA with a gigasample front end. Okay. Can we make these leaps? Can we use the same equations to then demonstrate things? Okay, because what I found is that once you've got the theory right and the theory done well, okay, implementation for these higher and more advanced things actually comes quite easily. And can we do that at the same time? And with that, thanks for listening, and look forward to chatting with you later.
Thanks very much, Chris. We've got about a minute for questions.
I am around, so if you need to chat. Yeah.
Tony, G3OVH.
Hi, Tony.
My day job before I retired was the radiation damage of CCDs and things like that. Now, unfortunately, you said commercially sensitive, etc. But can you say anything about how Raspberry Pis perform in low Earth orbit?
Yes, they perform very well. I've not seen one fall over yet with what I'm doing. Now, I'm doing something quite unique on this because for the work that I've done on Raspberry Pis, I actually have research that doesn't just look at the silicon to understand really where the damage goes, how you mitigate it, and functionally what do you do to change it in software. But also I have a PhD student who's been building a compiler for doing TMR of the caches and the processor registers. Okay, so there are some unique things added to that mix. I would add as well that the amount of ionizing dose that I have given these things is an order of magnitude bigger than what you would expect to see. Oh, you know they do. I test things till they die. Okay, I definitely do that. But if something is hitting hundreds of kilorads and it's still going, and we did that more than once, but that needs to come out in journals and articles and things, because it needs a lot more rigor to it, I think, as well. I think the science is preliminary. I think that the parts and the selection are good. You should do your own tests as well, but I'm still waiting to find an outlet of where we can publish this that has the right science behind it. Because I think for some of these things, they were kind of catch-all projects. So for instance, the radiation testing was done by a student called Matthew Mould. Thank you, Matthew. And the testing regime that we did was built off of another project before that, but incorporated a lot more of these processes. But because of the schemes and the things that we did to it, I think it's worth putting that all into one place, because I've tested things from the Pi 1 all the way up. I haven't really done anything with the Pi 4 yet. Sorry, that was a long answer.
A further question.
SD cards.
SD cards, yeah.
And Raspberry Pi.
Uh-huh.
Not necessarily space compatible.
No, I think they're okay. It depends what you're doing with them. So you can create Raspberry Pi images that are read-only. And so again, it comes back down to your mission need. Like, do you need to write things, or can they act as just routers and run everything in RAM?
Yes.
And especially if my RAM is TMR'd in software, my processor caches are ham error corrected, and my processor registers are duplicated.
Yeah, I was partly thinking of the mechanics.
No, I mean, even if you looked at the one that was released by SSTL, if I go back, I mean, that is literally just sitting there. Oh yeah, it is potted in, but no, it's not DP190'd in. You'll be shocked at how resilient COTS can be, and I'm sure there are other manufacturers and people in the room that I think have given it a shot. I know these things have gone down to 3,000 meters in oil underneath our oceans. Things that I know that some of these things have done. Okay, you just need to try. Okay, but like you say, try them, break them, figure out what needs to happen, and whether or not you can work with that. Because when I haven't put these things under Proton yet, or any high, high neutron thing, that's the next step that I'd like to do on these particular parts. And if they all fall over then, well then it's a case of, well, do I just fly 3 of these and just be done with it? Remembering then that I've got the software compiler thing, like that, it's the Proton stuff that actually I need more to confirm and properly validate my compiler.
Okay. Thank you. Thanks, Chris. Any other questions? Okay, we'll call it a day there. Chris, thanks very much.
Thanks, Tim.
We'll break now till 1:30.